The wrong picture of the atom, one of the most widespread myths in physics, is the idea that atoms look like miniature planetary systems. You have probably seen countless diagrams showing tiny electrons circling around a dense nucleus, just like planets orbiting the sun. This image is so familiar that it feels natural to believe it is correct, but it is not. This picture of the atom is a relic that has survived for more than 100 years. And the reason it persists is simple. Our brains find it much easier to imagine atoms this way than to accept the strange quantum reality of how electrons truly behave. The irony is that if atoms actually looked and worked like these diagrams, we would not be here to talk about them. Matter itself would be unstable and collapse in an instant. Rutherford's planetary model. The planetary model was first proposed by the New Zealand physicist Ernest Rutherford in the early 20th century. At that time, it was revolutionary. Rutherford's experiments showed that most of the mass of an atom is concentrated in a tiny nucleus, and that electrons orbit around it. The model was simple, elegant, and intuitive. It gave us, for the first time, a clear structure of matter at the atomic level. However, this model had a fatal flaw. To understand it, imagine spinning a bicycle wheel in water. As the wheel turns, it stirs the water, creating small waves and losing energy until it eventually stops. Something similar would happen to electrons in Rutherford's model. Because they are charged particles accelerating around the nucleus, they would emit electromagnetic radiation, lose energy, spiral inward, and crash into the nucleus. If this were true, all atoms would collapse in a fraction of a second. The very existence of stable matter would be impossible. This paradox made it clear that Rutherford's atom could not be the final word. Attempts to fix the model physicists like Niels Bohr, Arnold Sommerfeld, and Louis de Broglie tried to fix Rutherford's atom by adding new ideas. Bohr proposed that electrons could only occupy certain fixed orbits with quantized energies, jumping between them while emitting or absorbing radiation. Sommerfeld introduced elliptical orbits. De Broglie went further, suggesting that electrons could behave like waves. These theories improved our understanding, but still relied on the idea of electrons moving along specific paths. They were important stepping stones, but not the final answer. The real breakthrough came with Erwin Schrödinger. Using his new mathematical tool, the wave equation, Schrödinger provided a framework that solved almost all the problems at once. His model explained why electrons do not simply crash into the nucleus and why atoms are stable. What was wrong with the old picture? The fundamental mistake was assuming that electrons behave like tiny balls following a clear path. In reality, electrons are quantum objects. They follow the strange rules of quantum mechanics, which are completely different from the classical physics we experience in everyday life. One of the key differences is indeterminacy. In quantum mechanics, particles like electrons do not have a definite position or velocity unless we measure them. Instead, they exist in a state described by probabilities. An electron inside an atom does not follow a precise orbit. Instead, its position is spread out in space according to its wave function. Orbitals. The quantum reality physicists represent the electron's wave function as a cloud called an orbital. The orbital is not the electron smeared out like water. Rather, it shows the regions where the electron is most likely to be found if we measure it. Until we perform a measurement, the electron's exact position remains undefined within this cloud. This reality is very different from the neat circular paths shown in old diagrams. Instead of orbits, electrons occupy these orbital clouds, which can have a variety of shapes depending on the electron's energy and angular momentum. One of the most beautiful aspects of quantum mechanics is that these orbitals are not random. They have well-defined shapes that can be predicted mathematically. Even for the simplest atom, hydrogen, there are many possible orbitals. The 4 quantum numbers. Every possible state of an electron in an atom is described by 4 quantum numbers. These numbers label the electron's properties and determine the shape and energy of its orbital. The first number, n, tells us the electron's energy level. Higher values of n mean the electron has more energy and is, on average, farther from the nucleus. The second number, L, is related to the electron's angular momentum. The third number, m, corresponds to one component of that angular momentum in space. These ideas are very abstract because electrons in atoms do not rotate like planets. Angular momentum in quantum mechanics is a property of the electron's wave function, not of its speed along a path. In fact, the lowest energy state of the atom, the ground state, has Ltech 0, meaning zero angular momentum. Thinking classically, this would mean the electron is not moving at all, which makes no sense if we try to picture it as an orbiting ball. This is exactly why classical intuition fails. Beyond classical thinking, physicists sometimes use classical analogies as a teaching tool to make quantum concepts easier to digest. But deep down, we know electrons are not little planets. Their behavior can only be understood through the strange but precise mathematics of quantum mechanics. By embracing this new way of thinking, we uncover a hidden beauty. Orbitals can have spherical shapes, dumbbell shapes, or even more intricate forms. These shapes determine how atoms bond with each other, how molecules are formed, and ultimately how the material world exists. A quick pause. If you're enjoying this journey into the quantum world, make sure to like this video and subscribe to the channel. There are new science videos every week, and your support helps us keep exploring the universe together. The beauty of orbitals. Take a moment to appreciate how astonishing orbitals are. They are not just abstract shapes. They are a window into the fundamental structure of matter. Each orbital corresponds to a possible way the electron can exist around the nucleus. When we look at these patterns, we are looking at the very blueprint of chemistry and life. The diversity of orbital shapes is what makes atoms interact in countless ways, forming the complex molecules that make up everything from the air we breathe to the cells in our bodies. The takeaway. The old planetary picture of the atom is useful as a simple teaching tool, but it is deeply misleading. In reality, electrons do not move in neat orbits. They exist in states of probability, defined by wave functions and quantum numbers. This is why matter is stable, why atoms do not collapse, and why the universe can exist as we know it. Understanding this does more than just correct a misconception. It opens the door to appreciating the strange, beautiful, and often counterintuitive world of quantum mechanics. Reality at the atomic level is far stranger than we can easily imagine. Yet it is also far more beautiful. Orbitals reveal patterns and structures that govern the behavior of all matter. By letting go of outdated models, we can see the universe in a new light, one that is richer, deeper, and profoundly more accurate. Thank you for watching. If you enjoyed this deep dive into quantum physics, don't forget to subscribe and explore the other videos on the channel. There is an entire universe of science waiting to be discovered.